Hey everyone, welcome back to the dining room shop. So, taking you guys along for a quick experiment this morning. One thing that I've had to do a decent amount is sort of be a salesman for the precision ground flatstone. I'm sure most of my viewers are already familiar with them, but if you're not, of course, what I recommend to most people is to go and watch Robin Renzetti's amazing video on them. That's the closest thing that you can get to actually using one in real life and experiencing it to know how wonderful they are. But what I find is when trying to explain the concept of a precision ground flatstone to people, I have a hard time driving home the point that these really don't remove material. With the caveat that you're using them on a surface which is already flat and you're using them properly and everything is very clean. There seems to be some hesitancy to this belief, even amongst users of flatstones. But I tend to believe it's true. But we can't just believe things blindly. So I figured we'd do a series of tests to see just how true this is. This is, like I said, the first in the series. I've got a couple other things I want to try to sort of determine the behavior of flatstones and how they affect objects. But today what we're going to be doing is starting with gauge blocks. Gauge blocks are the quintessential thing where you really wouldn't ever want to hit it with an actual stone. But stone and gauge blocks, at least in my opinion and many others, is a perfectly safe thing to do. And in fact, you can revive quote-unquote dead gauge blocks. This particular gauge block here, you can see, had experienced some pretty brutal scratching at some point in its life. This is from a set I just recently picked up, but it was used. And so this block wouldn't ring. Normally, that would be that, right? Not much you can do about it. But after a few seconds on a flat stone, it's now repaired. I can ring it to other blocks just fine. So something's happening, and yeah, it's removing the burr that's been raised by that scratch. But the concern is, if you did this habitually, if you stoned your blocks every time you went to use them before you rung them, could you eventually over time change the size of the blocks? Like, down on the single-digit micro-inch level? That's what I'd like to find out. So I've got a little setup here that will hopefully let us test if we can detect anything. We'll zoom in and take a look at what we're doing here. So in order to detect what could be micro-inch level changes in block dimension, we need a really good gauging setup. So here's what we've got going here. Two gauge blocks, or two sets of gauge blocks. One is a stack, one is a singular block. I'll explain why in a moment. But we're looking at it with the Round & Sharp 599 981, the best indicator in the world, right? The nice flexure pivot, so there's no backlash or hysteresis or slop in the joint. A nice solid indicator stand. This is plugged into my old reliable Tessa electronic indicator amplifier. Now, this has 10 micro-inch resolution on the top scale. That's what we're looking at right now. But we want to be able to zoom in, and so I'm using the 16-bit ADC, which I've shown in many other videos, and put together a quick little program here which allows us to hopefully do some higher precision metrology. But first, the reason there's two gauge blocks, or two stacks, is we need to sort of get rid of the potential thermal influences, right? If we were to just, let's say, inspect the one gauge block, we could zero our indicator on this block, stone it vigorously for a while, and then come back and measure, put it under the indicator, see if the readings changed. And I'd be quite confident that the reading would have changed, just because I am not in a temperature-controlled laboratory. And, the things are gonna grow and shrink. This is a big indicator stand here. Who knows? I wouldn't trust that reading, we'll just say. However, if we do a comparative reading between two different sets of blocks, which are on paper the exact same size, then we sort of eliminate these potential thermal effects. As long as we let these come to equilibrium and make sure they're the exact same temperature, we no longer have to worry about thermal expansion over, long distances. We're really just concerned about the difference in temperature between the two. And even if there was a difference in temperature of maybe a few degrees or so between the two, the difference in block size would hopefully be very, very small. That's one of the reasons I'm using small blocks and not a 1 inch or 2 inch block is to minimize this effect. And in this way, we're only, basically the dynamic range of the reading and the precision we need is reduced. So we compare. What we're going to do here basically is 0 on one, the other should read the same, not exactly, but we'll look at that in a second. Then we'll stone one for a while, let them come back to the same temperature, and see if we can detect a difference between the two or change in the difference between the two. That's the setup. Now you'll notice these blocks are not sitting on the surface plate. They're in fact sitting on a flat stone. And what I found in my initial setup for this test is the flat stone is actually almost the most ideal sort of anvil or platen or whatever you want to call it for performing this really high precision gauge block measurement. I tried, of course, the surface plate first. Now this surface plate I know isn't the most flat thing in the world, so that's one reason I didn't want to use it. But even still, on a good area of the plate, I was having trouble getting consistent readings, or at least very repeatable readings. I then tried an optical flat as an anvil, same problem, worse actually. And even this ceramic anvil from a microcator stand still wasn't as repeatable as I would like. And really that's just because of sensitivity to contamination. If there's even a fingerprint on the underside of the block or the plate, that the amount of oil that gets deposited on the surface, when you try and move the block, it sort of piles up, makes a hydrodynamic wedge, and can make things move around, affect the parallelism, these sorts of things. So when we do it on a flat stone, the flat stone, right, acts as a wiper, and so you can get very good consistent contact with the block sitting on the surface and not have to worry about hydrodynamic wedge or anything like this. In theory, if you got these clean enough, it would work on like an optical flat or something, but it's just so sensitive to contamination. I find this to be the most repeatable, at least for a practical setup like this. So let's take a look at how we might take this measurement here, the program I've set up. So, like I said, we've got the two stacks. The right one is a 450 thou block. On the left, we have a stack of 150 and 300, adding up to nominally the same value. I've got it roughly zeroed on the actual box there, but what I can do in the program is hit 0, and it will zero it wherever the reading's at right now. What I can do then is come over to my other stack, put it pretty close to center, and then hit measure, and we'll get a reading there. So it reads that the stack is 7 microinches smaller. Now, this setup is not perfectly repeatable, so what I'm going to do is do this repeatedly. I'm going to come back to the first block, zero it again, so you can see the zero reading has drifted a bit. Now it's -12. Come back, take a measurement, 0 on the first one. Basically just minimizing the time for any sort of drift to occur between readings. So I'm going back and forth, zeroing on the first block and measuring the second stack. And I'll do this 2 more times.
Zero and measure.
Now what I can do is hit the average button and it will average the last 5 readings. So it's just saying that on average, the stack of 2 blocks is around 11 microinches smaller than the nominal 450 thou block. So what gives? This is kind of the cool part. You know, I don't think my indicator is erroneous by that much. But never take, if you're doing something that matters, you never just take the gauge block size for what it is. Any good set of gauge blocks comes with a calibration sheet. And in fact, this is a B grade set. So some of these blocks can have quite the bit of deviation to the point where that you really do need to consider this. So let's take a look at what we just measured. That 450 thou block, that actually is one of the best in this set. And that reads at 0. So it's within, you know, plus or minus 1 microinch of nominal value. Well, that block is perfect as far as the resolution of the inspection is concerned. Then for the stack, we've got, like I said, the 150 and the 300. So let's take a look. The 150 block is minus 20, and the 300 block is plus 8. So you add those together, and you would expect the stack of the 150 and the 300 to be minus 12. And then on top of that, you add the standard accepted value of the gauging film thickness to be about 1 microinch. And what do we get? Minus 11 from the nominal value. So I'm really pleased with that agreement between the reading that I'm seeing here and the calibrated dimensions of the gauge. But that's enough validation. It's time to destroy some gauge blocks, or hopefully not. So our stones today were generously provided by Spencer Webb, course of Kinetic Precision. He's the 6-inch PFG stones. Thanks to him for sending these over. I really needed a set. And we'll be stoning that 450 thou block that we just saw zeroed. That's how I'm going to say that I'm confident that this experiment will sort of yield hopefully no result or no noticeable change. I'm going to stone one of the most perfect blocks in the set, the +0, -0 block that has no deviation. Now, like I said, in order for this to work, everything does need to be meticulously clean. If your flat stones are at all greasy or oily, and same with the part, the guarantees are off. You know, for whatever reason, you very quickly develop sort of a lapping paste if your stones are very dirty, and that can scratch and wear things. But I've cleaned these off with IPA as good as I can. They're not perfect. I've cleaned this off very well, the block. And so I'm now going to stone this block basically as hard as I can for, I'll say, we'll do like a full minute, right? You would never stone a block for that long. And so I would say that represents, I don't know, maybe 50 to 100 uses of the gauge block on the stone, because in reality you'd never be doing this for more than a couple strokes. I'm going to stone it for a long time. I'll record the whole thing so you know it's not faked. We'll time lapse the footage, but you'll see me stone the block, and then we'll put it back up on that measurement setup and see if we can detect a difference. Okay, so that's a minute of stoning, good firm stoning, and I think we've got a problem here. I don't know if you can tell in the video, it looks like this stone has darkened a little bit. And looking at the block, there is some scratches. Now, why is this? This is not 100% clean. When I pulled this off, there was a residue on this, a film, that when I wiped it, sort of cleared the block up. So this is not 100% degreased. And if we do see a reading or a change in dimension, you know, clearly we saw some material removal. So this is not ideal. but I would posit that that's why. We'll measure this block, and then I'd like to repeat this experiment. I'm going to, I guess, clean this even better. Really, I don't have an ultrasonic cleaner, unfortunately, but degrease the heck out of it once again. And try the same thing on the other side, perhaps with the other stone here, and then see if that happens again. But it looks like we did we did something right. It's just, was this enough to be a problem dimensionally for this gauge block? So what I'm going to do now is set this so it's touching the other set of blocks, let it rest for at least a few minutes, maybe quite a bit longer than that, just to be safe, to make sure they're at the same temperature, and then we'll see if we can detect a difference. Okay, so blocks have been able to equalize for a moment here, or quite a bit more than a moment. Let's go ahead and take a reading and see what we see. So just as before, we will 0, move to the other block, take a measurement, come back, 0.
Move to the other block, measurement, and do this a few times.
Okay, averaged it out there, the last 5, and oh boy, that block's a different size now. So we're reading now minus 8.37, whereas before we were seeing minus 10.95. So the difference between the two blocks has decreased. This block used to be 11 microinches larger. Now it's 8.4 microinches larger. So it's a tough result. That block has changed in dimension. But like I said, I think that was because the stone was not clean enough. I mean, look at that, not good. What I've done is I've just, again, and hopefully better this time, tried to clean this stone again with IPA, get it as absolutely degreased as possible. And I'm going to repeat this experiment one more time. Take the same block, lap it for another minute in the exact same manner on this hopefully cleaner stone, and see what happens. Okay, round 2 of lapping is done, and we haven't measured it yet, but right off the bat, this looks a lot better, right? I think that may have been the problem, but I don't want to speak too soon. Let's throw it back on the indicator, let it soak, and see what it reads. All right, so the results are in. You'll notice the result from that last 5 reading was 8.25, minus 8.25. You notice, however, the one I did previously was 7.48, and yeah, it's not completely repeatable. So I averaged 5 readings 4 times and averaged those and came out to a value of minus 8. This is not the most repeatable setup in the world. But with that much averaging, I'm reasonably confident in that answer. So recall that before we got a result of minus 8.3, what was it, 8.37, I think? Yeah, minus 8.37, and now we see about minus 8. So perhaps we removed 0.4 microinches from the block that time, but I'm not completely confident in saying that could just be a measurement error, noise in the measurement. Either way, make your own decisions. But I think we did learn something today, which is that the cleanliness of your stones is extremely important to achieve this non-influencing behavior, right? If you don't want your stones to change the size of parts and remove too much material, make sure they're clean. That's why it's nice to have a shop set, which gets used on like machine tables and these sorts of things, and then a metrology set, which is perhaps only for gauge blocks and other really high precision gauges and these sorts of things. But I think we definitely have proven that cleanliness makes a difference, and that if used correctly, I think it's totally safe to stone your gauge blocks. Recall that this is me pressing very hard, stoning for a full minute on this block here. In normal use, if you just wanted to ring two blocks together, you really wouldn't do anything more than that. Maybe a few strokes, and that would be enough, just to make sure that maybe if you bumped this on something before, that there's nothing raised on the surface. So yeah, I think the amount of material that's appreciably removed, maybe over a career, you might want to get your gauge blocks recalibrated. But I think with good practice, it's a totally safe thing to do. That's just one of the tests I wanted to do today. Other things, are stoning a ground surface, right? That's a little different. These are lapped, so there's not much topography there to begin with. But when we stone a ground surface and we see that when we can see the high spots, that's those high spots getting burnished down. So I think it's a reasonable hypothesis to say that the worse the surface finish is starting off, the more your stones have potential to change the dimension, because they're starting at the amount of surface area that they're contacting to begin with is relatively small. Those peaks get flattened, and that could change sort of the average surface height. So I'd like to stone a ground surface and see if we can detect a larger reading there. I bet we can. But I don't think, it's also worth noting that I think the effect there is just from burnishing. I don't think we're actually removing material. But we can take a look at that. And then finally, I'd like to look at that ground surface and these surfaces as well with the white light interferometer. And so we can hopefully visualize, see the peaks and valleys from the ground surface to begin with, and then stone it, and hopefully we can see the effect of those peaks getting flattened. I'm waiting on a new microscope objective for the white light interferometer, so that experiment will have to wait. But yeah, I think this is some hopefully valuable information here. This is not like I said, not the best setup in the world, but hopefully we can glean some data from this. And yeah, hope that was interesting. See you next time.